Here's a challenge. Build me a polynomial that eats fractions and produces exactly the fractions. All of them. Nothing missing, nothing extra. Sounds harmless, right? Then try it with the simplest curve there is. Squaring. Feed it any fraction. Out comes another fraction. So far the challenge holds. But now try to reach the number 2. You'd need an input whose square is exactly 2. And that means the square root of 2, or its negative. Both irrational, famously. Watch the fractions crowd in on it. Closer, closer, always closer, and always missing. There's a hole in the crowd, exactly where we need a hit. Squaring keeps fractions inside the fractions, and still fails to reach them all. Staying inside is easy. Reaching everything, that's the real fight. Which polynomials win it? That's today's problem. Here's the exact question. Simple to state and brutal to settle. Find every polynomial with real coefficients whose image of the rationals is exactly the rationals. Exactly. That one word carries two demands at once. First, every rational input must land on a rational output. No leaks. Second, every single rational number must actually get hit by some rational input. No gaps. Two fronts. Most wrong answers to this problem come from fighting only one of them. By the end, you'll have the complete list, and, more valuable, 3 tools that crack a whole family of problems like it. Fair warning, the ending is a collision you can see coming, and still can't avoid. Facing a classification problem, a good first move, the move Polya would recommend, is to hunt for members of the club. Which polynomials are easy wins? Take a line. Multiply by a non-zero fraction, then add a fraction. Rational in, rational out. First front secured. And to hit any rational target you want, just solve backwards. Subtract, then divide. Both steps stay inside the rationals, so every target gets reached from a rational input. Second front secured. So every line with rational coefficients and a non-zero slope belongs to the club. Constants, by the way, die immediately. Their whole image is a single point. Here's the bold conjecture and the rest of this video. The lines are the entire club. Nothing curved survives. So how do you prove that nothing else works? You can't interrogate candidates one by one. There are infinitely many. You need filters, arguments that execute whole families at once. Here's the battle plan. 3 filters. Filter 0. Show that the coefficients of any surviving polynomial must themselves be rational. Sounds obvious. It isn't. Filter 1. Use pure shape, the way a polynomial's graph bends, to eliminate every even degree. And filter 2. The deep one. Use arithmetic, denominators, divisibility, to eliminate every odd degree from 3 upward. Whatever passes all 3 filters has degree 1. Let's earn each filter honestly, dead ends included, because the dead ends are where the method lives. Filter 0. Why would the coefficients have to be rational? Try the naive attack first. It teaches us something. Feed the polynomial 0. The output is the constant coefficient, and outputs are rational, so the constant coefficient is rational. 1 down. Feed it 1. Out comes the sum of all the coefficients. Rational again. For a line, those 2 facts pin down everything, and we're done. But for degree n, there are n plus 1 unknown coefficients, and each new input buys us only 1 equation. N plus 1 unknowns. Then let's feed it n plus 1 different rational inputs, and hope that n plus 1 values pin a degree n polynomial down completely. That hope has a name, and it's one of the sharpest tools in mathematics. Interpolation. A polynomial of degree at most n is completely determined by its values at n plus 1 distinct points. Why? Suppose two such polynomials agree at all of them. Their difference has degree at most n, and n plus 1 roots. Only the zero polynomial can afford that many. Same polynomial. Uniqueness. And Lagrange goes further. He hands you the recipe. For each node, build a small bump polynomial, equal to 1 at its own node, 0 at all the others. Look at what the recipe uses. Differences of the nodes and division by differences of the nodes. Nothing else. Rational nodes in, rational coefficients out. Now rebuild our mystery polynomial from its rational values. Rational values times rational bumps added up. Every coefficient lands rational. Filter 0, proved. Keep the rationals inside the rationals, and your coefficients are rational. Before moving on, was that lemma actually worth a proof? Test it against the world next door, the integers. Same question, one floor down. If a polynomial sends every integer to an integer, must its coefficients be integers? No! Here's the classic offender, the triangular number polynomial. X times x minus 1 divided by 2. Out of two consecutive integers, 1 is always even, so that product always splits by 2 cleanly. Integer in, integer out, every single time. But the coefficients? 1/2 and minus 1/2. Not integers. The lemma genuinely fails over the integers, and it holds over the rationals for one quiet reason. With fractions, you're allowed to divide. That's what rigidity means here. And keep this little polynomial in mind. It has one more part to play. Filter 1. Shape. From here on, our polynomial has rational coefficients and degree at least 2. Look at any even degree. Both ends of the graph shoot off in the same direction. Leading coefficient positive? Both ends climb, so somewhere in the middle, the graph bottoms out. A global minimum. And that's fatal. Every value below that minimum is never reached. Not by rationals, not by anything real. An entire half-line of targets, packed with infinitely many rationals, sits under the curve. Untouchable. Leading coefficient negative? Flip the picture. A global maximum, and everything above it goes unreached. Either way, coverage collapses before arithmetic even wakes up. Every even degree, from 2 upward, eliminated. By geometry alone. Odd degrees laugh at that argument. A cubic's 2 ends point in opposite directions. The graph climbs from minus infinity to plus infinity. And by continuity, it sweeps through every real height on the way. As a map on the real numbers, a cubic covers everything. The shape argument? Dead end. So interrogate the simplest suspect directly. X cubed. Can it hit the target 2 from a rational input? We'd need a fraction, in lowest terms, whose cube is 2. There's a classical filter for that. If a fraction in lowest terms is a root of an integer polynomial, its top must divide the constant term, and its bottom must divide the leading coefficient. Here, that leaves exactly 4 candidates. Plus and minus 1, plus and minus 2. Cube them. 1, minus 1, 8, minus 8. No 2. So x cubed is dead, but by a bespoke trick, one polynomial at a time. What actually killed it? Denominators. Let's industrialize that. Here is the engine of the whole proof. Our polynomial has rational coefficients, so multiply through by a common denominator and you get a twin with integer coefficients. Call its top one the leading coefficient. Now feed the polynomial any fraction, p over q, in lowest terms. And suppose the output is a whole number. Clear every denominator in sight. Then look at the equation, term by term. The right-hand side, a multiple of q. And on the left, every single term picks up at least one factor of q. Every term except 1. The lone survivor, leading coefficient times p to the n. So q divides that survivor. But p and q share no factors. Q can't touch p to the n. Conclusion, in green, q divides the leading coefficient. Read it again. Any rational input that lands on any whole number has its denominator dividing one fixed integer. That's the engine inside the rational-root-theorem, now running at full power. Let that sink in because it's a brutal restriction. The rationals are a dense crowd. Between any two of them, infinitely many more. But the rationals allowed to hit whole numbers? Their denominators divide one fixed integer, and fractions whose denominator divides one fixed integer form a grid. Evenly spaced points. One fixed gap between neighbors. 1 over the leading coefficient. Pull back from the crowd and watch the structure emerge. From a dense mist to a picket fence. Rigid, sparse. Marching down the whole number line at one unchanging step. This is all the ammunition our polynomial gets. To cover the rationals, it must in particular hit every whole number, 1, 2, 3, forever, and every successful shot must be fired from this fence. Keep that spacing in view. The finale is a duel between that fixed gap and a slope. Time to aim. One cleanup first. If the leading coefficient is negative, replace the polynomial by its negative. That flips the graph upside down, keeps every coefficient rational, and still maps the rationals exactly onto the rationals. Flipping signs just reshuffles them. So, odd degree, 3 or more, positive out in front. Past its last wiggle, such a curve climbs. Forever. And ever faster. Pick any whole number k higher than every bump on the curve. The horizontal line at height k crosses the graph exactly once. Everywhere else the curve is too low, and on the rising branch it climbs through once. One target, one crossing point, on the entire real line. But coverage demands that some rational maps onto k, and there's only one candidate. So that crossing point is rational, and any rational that lands on a whole number lives on the fence. One fence point per rung, marching up the branch. Now watch the collision. Two consecutive rungs, height k and height k plus 1. Their crossing points sit on the steep branch, 1 unit of height apart. How far apart horizontally? The mean-value-theorem answers 1 divided by the slope, somewhere in between. And the slope is exploding. The derivative of any polynomial of degree 3 or more grows without bound. So as k climbs, the horizontal gap between consecutive crossing points shrinks, and shrinks, towards 0. Eventually, smaller than the fence spacing. Look at it. 2 crossing points, forced closer together than 1 over the leading coefficient. And both of them must be fence points. Distinct fence points, which can never, ever be closer than exactly that. 2 different points of a rigid grid trapped inside a single gap. Impossible. There is no such polynomial. Odd degrees eliminated. Let's look back, the way you should at the end of any real problem, and march every suspect through all three filters. Constants? Their image is 1 point, dead on arrival. Lines with an irrational coefficient? Feed in 0 and 1. An irrational value falls out. Filter 0. Dead. X squared and every even degree? A global extremum strands half of the targets. Filter 1. Dead. X cubed and every odd degree from 3 up? The fence gap defeats the exploding slope. Filter 2. Dead. And the rational lines with non-zero slope? Both fronts checked directly, right at the start. Alive. The classification is complete, and it is beautifully small. The polynomials mapping the rationals exactly onto the rationals are the rational lines. Nothing curved survives. In is easy. Onto is the fight. 3 tools, worth filing permanently. 1. Interpolation as a rigidity principle. A degree in polynomial carries only n plus 1 degrees of freedom, so n plus 1 honest values pin it completely. That's how values force coefficients. 2. The denominator bound. Rational inputs that land on integers have denominators dividing the leading coefficient. You've met its little sibling, the rational-root-theorem. Same engine. 3. The pincer. Analysis controls growth. Arithmetic controls denominators. Hard problems fall where the two jaws meet. This problem is a classic. Mathematicians settled it long ago, and it keeps getting rediscovered because the pincer is so clean. Every source is linked below, so you can compare the standard write-ups with what we just built. Your turn. Same war, different battlefield. Find every polynomial that maps the integers exactly onto the integers. And careful, the ground has shifted. Remember our little friend x times x minus 1 over 2? Over the integers, it passes the first front without integer coefficients. Integer in, integer out. But watch its outputs. 0, 1, 3, 6, 10. The triangular numbers. It never says 2. Coverage fails, and proving that nothing curved can ever cover the integers takes exactly one idea from today's proof. Which one? That's the exercise. Post your solution in the comments. I'll pin the cleanest proof. And if you want your answer checked against the literature, the sources are linked below. If this kind of problem is your kind of fun, subscribe. A whole season of them is coming. Questions, alternative proofs, spotted gaps. The comments are open. See you in the next problem.